Hello friends, so today we are going to solve the question from heat and thermodynamics from the year 2014. We are going to solve two questions. Both those questions are from advanced, and from the year 2015 we are going to solve two questions from the advanced and four questions from the mains. So in total we are going to solve 8 questions. So the first question, which was asked in the 2014 advance, and it states that in the figure a container is shown to have a movable without friction piston on the top. The container and the piston are all made of perfectly insulated material, allowing no heat transfer between the outside and inside the container. The container is divided into two compartments by a rigid partition made of thermally conducting material that allows slow transfer of heat. The lower compartment of the container is filled with 2 moles of an ideal monatomic gas at 700 Kelvin, and the upper compartment is filled with 2 moles of ideal diatomic gas at 400 Kelvin. The heat capacities per mole of ideal monatomic gas are C of V 3R by 2 and C of P as 5R by 2, and those of ideal diatomic gas are C of V are 5R by 2 and C of P is 7R by 2. So based on this we are having two questions. Okay, so this is part A and we have a part B, and it states that first A part, consider the partition to be rigidly fixed so that it does not move. When the equilibrium is achieved, the final temperature of the gases will be. So basic figure is given to us, and it says that we have a piston. Okay, so this is a representation of piston, and it is able to move in the first case. Okay, and we have a rigid partition. Okay. So this is rigid partition. In the first case, this is rigid, it is not able to move, so only the piston is going to move. And it says that the under equilibrium, so heat is going to transfer from our, and it is says that lower is consisting of a monatomic, so there is a 2 mole of gas inside, and temperature is 700 Kelvin. Okay, and upper is of once again 2 mole, and there is a 400 Kelvin. Okay, and upper is having a monatomic, so this is our mono, and the lower one is our having a diatomic. So because of the temperature difference, the heat will be transferred to the upper side, and as the rigid is fixed one, so we can say that the volume of lower part is not going to change, so its volume will be constant. And because of the heat that is being transferred from the lower to the upper, and the piston is free to move, so there will be a expansion. Okay, so we can say lower gas is our constant volume and upper gas will be our constant pressure. And so let us start with the things which are given to us. We start with part A. And so for part A we are given that the partition is rigid. Partition is rigid, therefore from here we can say that its volume of lower part cannot change. Okay. So from here we can say the lower gas is at constant volume. Lower gas is at constant volume. Therefore, we can write that the heat lost or gained let us suppose that is our Q1, we will put N C of V, and final temperature minus initial temperature, which is ever given to us as 700. Okay. And this was for our lower compartment. Okay. Lower compartment. Now we come to the upper compartment. And upper compartment we have that the piston is movable. We are having movable piston. So we can say that pressure of the upper part stays constant. Therefore, we can say that heat gained or lost is our Q of 2. We can write this as our NC. Let me write this as NC of 1, and this is NCP of our 2. And this comes as a final minus 400. So we can use our conservation of energy because it is isolated system, which is our basically isolated system, or we can say no external heat. Therefore, let me write this as our N1 and this is our N2. Okay. So we can say that our Q1 is equal to Q2, which gives us our N1 CV1, and we have this as our this, because this will be 700 minus TF. So we get this as our 700 minus TF is equal to NCP2, and we have this as TF minus 400. Okay. And we simply substitute the values. We get this as 3/2 times R, and we have our 700 minus TF is equal to 2 7 by 2 R TF minus 400. Here this 2 R cancels out, and we get this as our, this will be 2100 minus 3 TF will be equal to 7 TF minus, and this will go 2800. Therefore we can say that this will be over 10 and 10, it will be over 49. So this will be, TF will be equal to 490 Kelvin. Okay, so this will be a final temperature. Now we come to our part B. It states that now consider the partition to free to move without friction, so that pressure in the gases in the both compartment is same. Then the total work done by the gases till the time they achieve equilibrium will be. Now the partition is also free to move along with our piston. Okay, so pressure in both the cases, it is said to be same. So we have our part B, and it says that so in part B we are having a free partition, which is also given that pressure is equal, and our movable piston. Okay. And we can say that our initially our piston is in mechanical equilibrium. Piston is in mechanical equilibrium. So internal pressure is equal to external pressure, and let us suppose that is our P naught. Okay. Now we can say after it reaches final equilibrium, we can say after equilibration, the final pressure is still our P naught. Okay. So pressure will be same. Therefore, we can write that the work done by the gases on the surrounding, or we can say our piston is W, which will be equal to our pressure and change in volume. Okay. And this change in volume will be of both because of our monatomic as well as our diatomic. Therefore, we can write that our W will be equal to our P naught, and this will be our first of all, let's write this in the form of our temperature and our pressure. Okay. So we can write that our P naught volume initial will be equal to our N1, R will be same, plus N2 R T2, and we can also write that our P naught final will be equal to our N1 plus N2 R times TF. Okay. So we can just write it as our work done W will be equal to our P naught, okay, this is volume final, and delta V, we can write this as our V final minus V initial. Okay. So if you multiply inside, so this will be coming as V naught V final, which we already have, and this will be our V naught multiplied by our V initial. Therefore, from here we get this is N1 plus N2 times R TF minus, and this comes as N1 R T1 minus N2 R T2, and R we can take as common, and T1 and T2 we already know, N1 and N2 we also know. Okay, so we can write that N1 and plus N2 will be over 4, so this comes as 4 and times R, so let us take as R is common, times TF minus, and this comes as our, let me put it inside the bracket, so this will be plus, and this will be about 2 T1, and that will be coming as 2 T1 is our 400, temperature is our 700 and 400. Okay, so this will be coming as our 2200, and this is our work done W, and we can write that our change in internal energy, that is our conservation of energy for isolated system. We can write this delta of U will be equal to we have this as N1 C of V1 Tf minus T1 plus we are having this N of 2 CV of 2 and Tf minus T2, and we just substitute the values, and this is isolated system. So according to our first law of thermodynamics, this change will be equal to our minus of W, and therefore we can write that this our N1 is our 2 N1 is our 2 multiplied by 3 by 2 R, and this comes as our Tf minus T1 plus 2 7 by 2 R, and this comes as a Tf minus T2, and this is equal to minus of W, which we already found out. So we substituted here is equal to minus of R 4 times Tf minus, this is our 2200. Here this 2 cancels out throughout and R also goes away, so we get this as our one second, this is 5, so we get from here this will be 3 Tf and this is 5 Tf, giving us 8 Tf minus 3 T1 plus 5 T2, this will be minus of 5 T2, and is equal to, this will be our minus 4 Tf plus 2200, and we get this as 4, this will be 12 Tf will be equal to, we substitute value of T1 as well T2 and 2200, this will be equal to 6300, and Tf is our 525 Kelvin. Now we can easily find out our work done. So we say work done will be equal to our R times 4.525 minus 2200, which gives us minus 100 R. So this is the work done. Okay, so it's a negative sign, so it means work is done on the gases. Okay, so we can say that net work is done on the gases. Okay, so we get this as, okay, so this was our minus of this and this was 490. Okay, so option D and D, both are D and D. So let me put it here. So we can see our option D is correct. and here also option D is correct. Next question. One second. Yes. This was asked in the 2014 advance, and it states that a thermodynamic system is taken from an initial state I with internal energy Ui 100 joule to a final state F along two different paths IAF and IBF as schematically shown in the figure. The work done by the system along the path AF, IB, BF are 200, 50 and 100 respectively. The heat supplied to the system along the path IAF, IB and BF are QIAF, QIB and QBF respectively. If the internal energy of the system in the state B is 200 joules and for QIAF is 500 joules, find the ratio of QBF and QIB. So basic PV diagram is given to us. So we have initial state I, final state F, and it goes from two paths. One is through our path A and another one is from our B. Okay. And we have to find out the ratio of our energy between this QBF and QIA, okay, between these two, okay, path for IBF. So here we are going to start with our first law of thermodynamics and then solve it for individual paths. So we have our from first law we can write that delta of U is equal to our Q minus W, and we are given that initial energy for at I state is 100 and for at point B it is given as 200. Total energy for our path IAF is said to be given as our 500. Okay. And the work done is also given to us. So work done for the path AF is given. So WAF is given to us 200. WIB is given to us 50 and WBF is also given to us as 100. So let us start for our I to F. Okay. So we can say from I to F, but in this case we are going to use path as IAF. Okay. So we can just use a thermodynamics law, first law, and this gives us that our U final, U initial will be equal to our heat for our path IAF and minus work done, because our this path between I and A, it is a constant volume, so work done for this path will be 0, so only the work done for path will be for our AF, so it will be minus work done for the path AF. Okay. Because work done for IA will be equal to 0 as it is constant volume. Therefore, from here we can say that our UF will be equal to, we are going to substitute the values, we get this as 100, IAF is 100, WAF is 200 this is our minus 200 plus U of I is our 1 second. WAF, WIB is 50, WBF is 100, UI is 100, UB is 200, and QIF is 500. Okay, so here I have written this as 100, so this will go 500, and UI is our 100, so this comes as plus 100. So we can say that our energy at final will be our 400 joules. Now we come from AI to B. You can say path from I to B. Same for a thermodynamics law, we are going to just expand it. So we can write this as U of B, U of I will be equal to our QIB minus WIB, and we get our QIB will be equal to our UB minus UI plus WIB. We substitute the value and we get this as QIB will be equal to our 200 minus 100 plus 50, which gives us the QIB will be equal to 150 joules. Now we come to our path, that is BF. So you can say from B to F, we can write that our UF minus UB will be equal to QBF minus WBF. Therefore, we can say that our QBF will be equal to our UF minus UB plus WBF, and we get this as our 400 minus 200 plus 100 is equal to 300 joules. Now we can easily find out the ratio. So we can say our QBF upon QIB will be equal to 300 and 150. This goes by 2. That is the option. Okay, the ratio is our 2. Next question. It was asked in the 2015 advance, and it states that a container of fixed volume has a mixture of 1 mole of hydrogen and 1 mole of helium in equilibrium at temperature T. Assuming gases are ideal, the correct statement is or are. So here we have to find out basically their average energy, a ratio of the speed of the sound, a ratio of the RMS speed of atoms, and part D is also, but the answer is different in case 1 by 2 and 1 by square root of 2. Okay. So we are given two gases, hydrogen and helium, and both are having 1 mole. So we are having our hydrogen, which is basically diatomic, and molar mass of hydrogen is our 2 gram per mole, and the degree of freedom, that is value of F, is our 5. 3 translational and 2 rotational at a typical temperature. And secondly, we are having helium. Helium is our monatomic. And molar mass of helium is our 4 gram per mole, and its degree of freedom is 3, which is translational only. Okay. Number of moles for both are given to us 1 and 1. And we start with option A. It states that the average energy per mole of the gas mixture is 2 RT. We can say option A, and we know the standard formula that our average energy of ideal gas per mole is our F upon 2 and multiply by RT. Okay, where F is our degree of freedom, T is the temperature. So we can write this same formula our two gases. For our helium, this will be our 3 by 2 times RT, and for our hydrogen, this will be our 5 by 2 times RT. And total energy will be equal to energy for helium plus energy because of hydrogen. So this comes as 3 by 2 RT plus 5 by 2 RT, and this comes as 8, and 8 goes by 4, so this comes as 4 RT. And in the mixture total moles, we can say that our total moles in mixture, that is N, will be equal to for N for hydrogen plus N for our helium, which is 1 plus 1 giving us 2. Therefore our average energy per mole in mixture, let us suppose we call this as U average, will be equal to our U total divided by number of moles, total number of moles, that is N. So this is our 4 RT divided by 2, so 4 goes by 2 giving us 2 RT. So option A is correct. Option B, and option B talks about the ratio of the speeds, and we know the formula that the speed V is equal to gamma RT divided by their molar mass and its square root. Okay, where gamma is our adiabatic index, which is equal to our 1 plus 2 upon F. Okay, and so we can write for our helium, velocity for our helium will be equal to gamma helium R of T and molar mass of helium and its square root. And gamma helium we can calculate, we can say our gamma helium will be equal to 1 plus 2 upon degree of freedom is over 3. So this comes as 5 upon 3. So we can write this as 5 upon molar mass is 4 gram. So this will be 0.004, and this comes as 5 upon 3 RT and its square root. Okay, and here we have to find out the ratio. Okay, we keep it as it is. Later on we can just simplify, and we can write that for our gamma for our hydrogen will be equal to 1 plus our one second. Okay, it is a gas mixture for the helium, so we do not need the gamma for hydrogen. And now we come to our mixture part. Okay. Therefore we can say that speed of sound in the mixture for calculation of this we need effective molar mass, and adiabatic index. So first of all, let's find out the effective molar mass, and then we are going to find out effective adiabatic index. Effective molar mass, let us call this as M mix. This will be equal to our molar of number of moles for hydrogen multiplied by molar mass of hydrogen plus number of moles for our helium, molar mass of our helium plus number of moles for hydrogen, divided by number of moles for hydrogen and number of moles for helium. Therefore we get this as effective molar mass, that is M mix, will be equal to, this is our 1 into 2 plus 1 into 4 and 1 plus 1, which comes 6 by 2. With this will be giving us 3 gram per mole, or we can write this will be over 0.003 kg per mole. Now we come to the effective adiabatic index. Effective adiabatic index, and for effective adiabatic index we can write this as our gamma for mix will be equal to our C of P for our mixture as well as C of V also for our mixture. Okay. So let's find out C of V for mixture. From P we can easily calculate. Therefore we can say that our C of V for mixture will be equal to our number of moles for hydrogen and C of V for our hydrogen plus number of moles for helium and C of V for our helium, and we come this as divided by their summation moles. So this will be equal to divided by 2, and this comes as 1 5 by 2 times r plus 1 plus 3 by 2 times r, and this comes as our 5 8, and this is 4. This will be coming as 2r, and for C of P of our mix will be equal to C of V of our mix plus R. This gives us 2R plus R, giving us 3R. Now we can easily calculate gamma adiabatic index for our mix. Is our C of P is our 3R, C of V calculated is our 2R. So there it comes as our 3 by 2. Therefore, velocity for our mix will be equal to adiabatic index for our mix R multiplied by T and molar mass of our mix, which gives us our 3 by 2 RT, and this comes as 0.003 and its square root. Now we just need to find out the ratio. We get V of our mix and V of our helium will be equal to, and we have this as our 5 by 2 RT divided by, for helium it was 0.004, and for our mix this comes as 3 by 2 RT, and this comes as 0.003 and its square root. This RT and RT cancels out, and we can write this will be equal to over 3 into 2 multiplied by 0.004, and this comes as our 5 into 2 multiplied by 0.003 and its square root. So here this 2 and 2 cancels out, and this will be coming as 12 divided by 15. Hmm. 12. One second, something is missing. Five by 3 for helium, I think. Yes, this is missing. This is 5 by 3, and this comes as our 3 and this comes as our 2. So this will be coming as 36 divided by 30. And the ratio is our square root of 6 upon 5. So option B is also correct. Option B is correct. Now we come to option C. RMS speed ratio is 1 by 2. Okay. So we know the relationship that our VRMS is equal to 3 RT divided by M and its square root. So we can just find out the ratio because we know all the values. So we can say that our VRMS for our helium divided by VRMS for our hydrogen will be equal to square root, and this comes as our 3 RT molar mass of helium, and we have this as 3 RT divided by molar mass of hydrogen, which can be written as, because 3 RT cancels out, so this comes as our molar mass of hydrogen divided by molar mass of helium. Okay, so this comes as our 2 upon 4 and its square root, which will be equal to 1 upon square root of 2. Okay. So option C is incorrect, but option D is correct because it is written 1 upon square root of 2. So you can say option C is incorrect, but D is correct. Next question. It was asked in the 2015 advance, and it states that two spherical stars A and B emit blackbody radiation. The radius of A is 400 times that of B, and A emits 10⁴ times the power emitted from B. The ratio of lambda A to lambda B of their wavelengths lambda A and lambda B at which peaks occur in the respective radiation curve is. Basically, we have to find out their radiation, you can say ratio, and lambda A, lambda B are called as a peaks, so which is nothing but the maximum value of their wavelength. And for that, we are going to start with the Wien's displacement law. So we can say that our Wien's displacement law, and we can write that Wien displacement law, it gives us our lambda max times temperature. The product is equal to B, where B is a Wien's constant and its value is known to us. So the maximum wavelength for A is given as lambda A, so we can say lambda A is equal to B upon temperature TA, and we can say lambda B is equal to B upon temperature B. So from here we can say that ratio lambda A upon lambda B is equal to, this will be coming as B upon TA and B upon TB. This B and B goes away, and this comes as our TB upon TA. Basically, we have to find out the temperature, and for that we are going to use Stefan-Boltzmann law. Stefan-Boltzmann law, which gives us that the power is equal to rho A T raised to power 4. Rho is a Boltzmann constant, A is the surface area, and T is the surface temperature. And for our surface area, we can write that value of area is equal to over 4 pi r square. So we have our two bodies. One is PA. So PA is equal to over 4 pi Ra square T raised to power Ta raised to power 4, and Pb is equal to constant 4 pi Rb square Tb raised to power 4, and we are given that power of A is equal to 10 raised to power 4 times Pb. Therefore, we substitute them, we can get this as constant 4 pi Ra square Ta4 is equal to constant 4 pi Rb square and Tb raised to power 4. So here this constant 4 pi cancels out, and we get that we get this as our Ta upon Tb whole raised to power 4 will be equal to our radius of B, radius of A whole raised to power square, and this is given to us as a 400. So we get one second, I missed I think something. Yes, I missed 10 raised to power 4. So this comes at 10 raised to power 4 and into 10 raised to power 4 is equal to, and we are given that our Ra is 400 times Rb. So this comes as Rb, and we have this as 400 Rb and whole raised to power 2 multiplied by 10 raised to power 4. Rb and Rb cancels out, so this comes as 16. Yes, so we can write that this will be equal to our 10 raised to power 4, and we can write this as 1.6 into 10 raised to power 5, which will be 1 upon 16. And so this is our Ta upon Tb whole raised to power 4, and from here we get this as Ta upon Tb is our fourth root of 1 upon 16, giving us 1 upon 2. So we get lambda A upon lambda B is equal to Tb upon Ta, which gives us 2. So we are supposed to find out the ratio. So the ratio is our 2. Next question. It was asked in the 2015 mains, and it states that consider a spherical shell of radius r at temperature T. The black body radiation inside it can be considered as an idle gas of photons with internal energy per unit volume small u is equal to capital U divided by V, which is proportional to T raised to power 4, and pressure P as 1 upon 3 U upon V. If the shell now undergoes adiabatic expansion, the relation between T and R is. So we are given that internal energy per unit volume is given to us, so it means small u is given to us as our capital U upon V, which is proportional to T raised to power 4, and pressure P is given as 1 upon 3 U upon V, which can say 1 upon 3 times small u, and the expansion is said to be adiabatic expansion. adiabatic expansion. So okay, so we can say that our internal energy U per unit volume, that is U is given to us as capital U V, and it is proportional to T raised power 4, so which we can write as A T raised power 4, where this A is our constant. Any constant doesn't matter. Therefore, our total internal energy that is capital U will be equal to small u multiplied by volume, which comes as our A T raised power 4 times V, that is volume. Similarly, we can write our pressure that is our P is equal to 1 upon 3 U raised power V, which is equal to 1 by 3, and we can write this as A T raised power 4. And basically it is spherical shell, so we can say volume for spherical shell volume, that is our V is equal to 4 by 3 pi r cube, or we can say it is proportional to r cube. And we are having adiabatic process. So we are having adiabatic process, and therefore we can write that our no heat exchange, or we can say our dq will be equal to 0. And thus we can write the state equation can say our state equation, that is where P will be equal to, which is already given to us, 1 by 3, and is our U is equal to 1 by 3 A T raised to power 4, and our internal energy, that is our U will be equal to A T raised to power 4 times volume. Now we can use our adiabatic relation for our first law of thermodynamics. Okay. So we can say from first law, we have our d of u is equal to dq minus p dv. dq 0, so this goes away. So we get our du will be equal to, sorry, this is capital, not small. du is equal to minus p dv. Okay. And u already we know, so we can just derivate it. So we can say our u is equal to a t raised to power 4 times v. Therefore we get d of u is equal to, we take its partial derivative, a is our constant, so we come this as 4 t3, and we have this as dt times v plus T4 times dV. And we come to the pressure part now. So our P is equal to 1 by 3 A T raised to the power 4. So we get minus P dV will be equal to minus minus P dV will be equal to over minus 1 by 3 A T raised to the power 4 times dV. We simply substitute value of our P. Now we substitute this into our equation. Therefore, we get our A 4T cube V dt plus T raised to the power 4 dV is equal to minus 1 by 3 A T4 and dV. And our A goes out throughout, and T3 will also cancel, so this comes 3, this left 1, and this is also left with 1. So we are left with only our 4V dt plus T dV is equal to minus 1 by 3 T dV. And we combine this dV and dV, so we get this as our 4V dt plus this will be 1 plus 1 by 3, which will be 4 by 3 times d dV is equal to 0. We can just separate the variable because 4 cannot be equal to 0. We can just ignore it, and from here we get that our dt by t plus 1 by 3 dV by V is equal to 0. And volume we know is directly proportional to our R cube. We know that our volume is proportional to our R cube. Therefore, we can write that dV by V will be equal to d of our R cube, and volume is our R cube. This gives us, this will be 3R square times dr and divided by R cube. So square goes by this cube, so this comes as our 3dr R, and we substitute in place of our this dV by V. So we get this as our dt by t plus 1 by 3. This comes as our 3 dr R is equal to 0. 3 and 3 cancels out, and this gives us our dt upon t plus dr upon R is equal to 0. And we simply integrate them. We get this as a natural log of t, and minus natural log of R plus C. So from here we can say that our, we can just combine it, natural log of TR is equal to C, or we can say that our TR product will be equal to, this comes as our natural log we can take on other side. C is a constant, so this will be our e raised to power C, that will be another constant. Therefore, we can say our T is inversely proportional to our R. So we have option C is correct. Option C is correct. Next question. It was asked in the mains 2015, and it states that consider an ideal gas confined in an isolated closed chamber. As the gas undergoes adiabatic expansion, the average time, it should be time of collision between the molecules increases as V raised to power Q, where V is the volume of the gas. The value of Q is, gamma is our adiabatic, you can see index. Second. Okay, and we are going to start with our basic formula, that for our mean free path, that's our lambda is tau is equal to lambda upon V. So we can say our mean free path, which is given as tau is equal to lambda upon V, okay, where V is the average velocity, and this mean free path in terms of our distance can also be written as, lambda is the mean free path and tau is our collision time. My mistake, 1 second. So we can say mean collision time. Mean collision time, that is our tau, and our lambda is our mean free path. Lambda is equal to 1 upon square root of 2 pi d square and n. Okay. Here d is the molecular diameter. D is our molecular diameter, and n is our number density. N is our capital N divided by V. It is called as a number density, where capital N is number of molecules and V is the volume. Okay. So we can say capital N is our number of molecules and capital V is our volume. So from here we can say that our N is inversely proportional to our volume. Okay. Therefore, we can write that our lambda is directly proportional to our volume. Okay. And the average molecular speed which we denote as our VRMS will be equal to 3 kT divided by m square root. And so from here we can say that our we also know that our V average is proportional to our VRMS, which is proportional to our square root of temperature. Therefore, we can say that our tau, which is our lambda upon V, will be proportional to volume upon square root of temperature. Okay. And we are said to be this as adiabatic expansion, so we are going to modify, because we need the relationship between the volume and temperature. Then we can just substitute T by V, because in the question tau is given as volume raised power Q. Okay, so everything has to be in volume. So we can say that for adiabatic expansion, we know that our TV raised power gamma minus 1 is equal to constant. Okay. And where gamma is our adiabatic index. Therefore, we can write that our T is proportional to 1 upon volume gamma minus 1, or we can write the proportional to V 1 minus gamma. And we need square root of T, so we can say our square root of T is equal to V 1 minus gamma whole raised power 1 by 2. Or we can write this will be equal to V 1 minus gamma divided by 2. Okay, now we are given that we found out that tau is our V upon square root of T. Therefore, we can write that our tau is proportional to V upon square root of T, which is proportional to V upon V 1 minus gamma upon 2. And this we can rewrite as V 1 minus gamma minus 1 upon 2. And this gives us V, and this will be 2 minus 1 plus gamma, or we can say 1 plus gamma upon 2. And we are given that this is equal to V raised power Q. Therefore, we can say that our Q is equal to 1 plus gamma upon 2. Option C is correct. Correct. Next question. It was asked in the 2015 advance, and it states that an ideal monatomic gas is confined in a horizontal cylinder by a spring-loaded piston as shown in the figure. Initially, the gas is at temperature T1, pressure P1, volume V1, and spring is in its relaxed state. The gas is then heated very slowly to temperature T2, pressure P2, volume V2. During this process, the piston moves out by a distance x. Ignoring the friction between the piston and the cylinder, correct statement are. So we have to find out. We have given various conditions for our temperature and volume, which are same for all. For A and B, volume is initial in volume, it is 3 times, temperature is also 3 and 4 times. We have to find out the energy stored, change in internal energy, work done, and heat supplied. So this is entire, you can say, basically based on our conservation principle. Okay. And So the gas is said to be monatomic, therefore we can write that internal energy that is our U is equal to, this is our F upon 2 nRT. Okay, so degree of freedom is our 3, therefore we can write that our internal energy will be equal to 3 by 2, and number of moles are not given, so we can say this as our nRT. And we have our initial state, and for the initial state we are given pressure as P1, volume V1 and temperature T1, and we are having final state, and we are having our pressure P2, volume V2 and temperature T2. And for our final state we have to remember, let me draw the approximate diagram for that. So this is our initial position of the piston, it moves towards our right through a distance of x, so this becomes the final position of the piston. Okay. And we are going to have a spring which will be compressed, okay, because spring is connected to a fixed point. And we assume that if A is the area of our this piston, okay, so in this case if, okay, let me, because this everything is closed, so we are going to have initial volume, and our initial volume will be only this much, this will be V1, but our volume, final volume, that is our V2, will be our this much. Okay. And we can say from here that our final volume is our V2, which will be equal to V1 plus, let us suppose this is our extra volume, and this extra volume will be equal to A multiplied by X, so it will be V1 plus A times X. So from here we can say that our X will be equal to V2 minus V1 divided by area, and we are having ideal gas, so we can say that our for ideal gas we can write, we have two position, initial position and final position, so we can write our for ideal gas PV is equal to nRT, and we can write this formula for our initial condition, that is our P1 V1 is equal to our nRT1, and also for our final position, that is our P2 V2 is equal to nR times T2. And this is monatomic, so the specific heat, a molar specific heat, we can easily, we know rather. Okay. And this entire will be, you can say, because initially, so this is suppose our initial state, so here the spring is relaxed, so basically means the pressure which is inside will be entirely balanced by the spring. Okay, because initially the spring force is equal to 0. So we can say that spring force, here we have to remember, this was my mistake, because spring was relaxed here, so this entire internal pressure will be balanced by the external pressure which is inside here, not by the spring, because spring is relaxed. So we can say spring force and pressure balance. So you can say that our spring is relaxed, therefore force exerted by spring is 0. Force exerted by spring will be 0. Okay. And because in the here the pressure is actually not mentioned, what is the situation of pressure on this side, so we are going to call this as a P external for the sake of convenience. Later on we can just sort it out. Okay. Therefore we can say that in the initial state here pressure is our P1, and here we call this as a P external. Thus we can write that our P1 is equal to P external. Okay. Now the piston moves by a distance x. Piston moves by distance x. So spring will be compressed. Spring is compressed. Therefore force due to spring will be equal to its constant and distance through which it is compressed, that is our x. So now there will be a pressure due to the spring, so we can say our pressure, let me write it this way, additional pressure on the piston due to spring. Additional pressure due to spring on piston, which we call as P spring, will be equal to force spring divided by area, which comes as kx upon A. X we already know, therefore we can write that PS will be equal to K V2 minus V1 upon A square. And in the final state also this entire system is in balance. So basically means the external pressure and our spring pressure is going to balance the pressure because of the entire system, okay, which is our P2 now, okay, because for this entire thing the pressure is given as P2. So we can say that our pressure force equation internally we have our P2 pressure and area is A will be equal to P external, area is A plus K times X, and we know that our P external is equal to our P1. And one second. Okay, so we can just write in the form of our pressure entire thing. So we can say our P2 is equal to our P1 plus this comes as K V2 minus V1 upon A square. And so let us denote, because this K is a constant, A area itself is constant, therefore we can write that P2 is equal to P1 plus a constant K and V2 minus V1, where we can say this constant K is equal to K upon A square is some kind of constant. And now let us evaluate each of the option. Okay. So we are given option A. Option A states that V2 is equal to twice V1 and T2 is equal to thrice T1. V2 is equal to twice V1 and T2 is equal to thrice T1. And it is asking the energy stored in the spring is, 1 by 4 P1 V1. Okay. We know the standard formula that energy stored in spring, that is U of S, will be equal to 1 by 2 K X square. X we already know, so we get this as our U of spring is equal to 1 by 2 K, and this is our V2 minus V1 A and whole square. So we are given V2 is twice of V1, so we get this as our V2 is, so we get this as our half of K and V1 square upon A square. One second. Yeah, K V1 square upon A square. Okay, and let me differentiate it, because here it will be a little bit difficult. So let me call this constant as K prime. K prime is equal to spring constant divided by A, and here it will be our spring constant, and okay, therefore we can write this will be equal to over half, and K is equal to over K prime A square V1 square upon A square. So this A square and A square cancel out, so we get our spring is equal to over half K prime, which is our V1 square, and we know that our K prime we can just calculate. We can write that our P2 is equal to K prime V2 minus V1. So V2 is given as twice of V1. So this comes as K prime, sorry, I missed one thing, P1 plus. So this comes as our P1 plus K prime upon V1. Okay. And from ideal gas law, we can write, or we have already written, that P1 V1 is equal to nR T1 and P2 V2 is equal to nR T2. Therefore, we can write that our P2 is equal to nR T2 upon V2, and temperature is said to be given as our 3 times T1. So this comes as our nR 3 times T1 and 2 times V1. So this giving us 3 by 2, and we have this as nR T1 upon V1, which comes as 3 by 2 P1. Therefore, we already know now the relationship between our P2 and P1. So we substitute P2 and we get this as our 3 by 2 P1 is equal to P1 plus K prime V1, and this gives us K prime V1 is equal to 3 by 2 minus 1, which will be our 1 by 2 times P1. So we get that our K prime will be equal to P1 upon 2 times V1. Okay. So in case of spring, we can just substitute our K prime now. So we get our energy of our spring, which was our 1 by 2 K prime V1 square is equal to 1 by 2 P1 twice V1 square, and this V1 square cancel out by the V1. So we get this is equal to 1 by 4 P1 V1. So option A is correct. Option A is correct. Now we come to our option B. And same condition, option B, V2 is twice V1 and T2 is thrice T1, but now we have to find out change in internal energy, which is quite simple now. So we can say our delta U will be equal to our U2 minus U1, which comes as our 3 by 2 nR T2 minus 3 by 2 nR T1. So we can write this as our 3 by 2 nR is our comma T2 minus T1, and we get this as our 3 by 2 nR. T2 is given as 3 times T1, so this comes as twice T1, and this 2 and 2 cancels out, so this comes as our 3 nR T1, and we know already that our P1 V1 is equal to nR T1. Therefore, delta U is equal to nR T1. We can put just as our P1 V1. So option B is also our 3P1 V1 is correct. And now work done and heat. Okay, 3V1 and 4T1. So option B is correct. Now we come to our option C. Option C gives us that our V2 is our 3V1 and T2 is equal to 4T1. We have to find out the work done. Okay. So work done by the gas is our W integration, and this is our V1 V2. Okay. And P is our gas pressure, which is equal to, we already know. Okay. So this P, let me write it here, this P is our gas pressure, and we already know that our P is equal to pressure external plus K upon A times X, which comes as our P1 plus K upon A square V minus V1. Okay. Because volume we have taken as V now, because of the integration we are going to change it. And we substitute in terms of K prime, so we get this as our P is equal to P1 plus K prime V minus V1. Therefore, work done between V1 and V2, we get this as P1 K prime V minus V1 and D of V. Okay. And this is now integral, quite easy. So we can say our W is equal to, this is our P1, and we are going to get this as V2 minus V1. Okay. And plus second integral, let me solve it separately. This is our V1 V2 K prime V minus V1 and dV. So we can substitute it. This right as V1 V2 V minus V1 and D of V. And let us assume, for solving it, we can say that our V minus V1 is equal to U. Therefore, we get D of V is equal to D of U, and limit will be now 0. Okay, limits are easy to calculate. This is our V goes from V1, so this will be U is equal to 0, and then will be V2 minus V1, and we have this as our U D of U, which comes as our U square by 2, and this comes as 0 V2 minus V1, which comes as our 1 by 2, and this is our V2 minus V1 and whole square. So therefore work done will be equal to P1 V2 minus V1 plus K prime upon 2 and V2 minus V1 whole square. We are given that V2 is equal to 3 times V1. We are given that our V2 is equal to 3 times V1. So we substitute them. W is equal to P1 and this comes as twice V1 plus, and we have our K prime by 2, and this will be coming as our twice V1 whole square. And let's calculate our this K prime. And once again we know that our P2 V2 is equal to NR T2. Therefore we can say our P2 is equal to NR T2 upon V2. T2 is given as 4 times T1. So this comes as NR 4 times T1 and V2 is given as 3 times V1. So we get this as 4 times 3 NR T1 upon V1, and this entire will be equal to P1. So we get our P2 is equal to 4 by 3 times P1. Now we come to our standard relationship, that is our P2 is equal to P1 plus K prime V2 minus V1, and V2 is given as 3 times V1, so this comes as P1 K primes 2 times V1, and P2 is 3 times 4 by 3 P1, so we get this as our 4 by 3 P1 is equal to P1 plus K primes twice V1. So we get this as K prime will be 1 by 3 and 2 V1, so this will be a P1 upon 6 times V1. And now we can just substitute here. So we get our work done will be equal to P1 twice V1 plus 1 by 2 P1 6 times V1, and we have this is twice V1 whole square. Okay. And let me open the square. So this comes as 2 square and V1 square. So this V1 cancel with this square, and this 2 goes by this square and 2 goes by this 3. Therefore we get work done will be equal to twice P1 V1 plus 1 by 3 P1 V1, which gives us 6 plus 1, that is 7 by 3 P1 V1. Okay. So we have option 3. I think that is also correct. Option C is also correct. And finally we have heat supplied under the same condition. So option C is correct. Is correct. Now we come to option D. Volume and temperature are same. V2 is equal to thrice V1 and T2 is equal to 4 times T1, but we have to find out the heat supplied. So first law of thermodynamics. So we can say from first law, we have that Q is equal to internal energy change plus work done, and our internal energy change, that is delta U, is our temperature dependent. So this is our 3 by 2 nR and T2 minus T1, which we have already written also, but here the value of temperature will be different. T2 is 4 times T1. This comes as 3 by 2 nR 4 T1 minus T1, which gives us 9 by 2 nR T1. But we know that P1 V1 is equal to nR T1. Therefore, delta U is equal to 9 by 2 n, sorry, not n, but simple P1 V1. So this is our internal energy. Work done we already know is our 7 by 3 P1 V1. Okay, so we substitute. So we get our Q is equal to 9 by 2 P1 V1 plus 7 by 3 P1 V1, and this is our 6 will be our LCM, and it will be our 27 plus 14 P1 V1. So get Q is equal to 41 upon 6 P1 V1. So the heat supplied is our okay. So option D is incorrect because it is 17 by 6. Okay. So option D is incorrect. Incorrect. Next question. It was asked in the 2015 mains, and it states that a solid body of constant heat capacity 1 joule per degree centigrade is being heated by keeping it in contact with reservoirs in two ways. Both are sequentially keeping in contact with two reservoirs such that each reservoir supplies same amount of heat, sequentially keeping in contact with 8 reservoirs such that each reservoir supplies same amount of heat. In both cases, the body is brought from initial temperature of 100 degrees centigrade to a final temperature of 200 degrees centigrade. The entropy change in the body in both cases respectively is. Okay, so we have a body which is, so we have two cases. So in the first case, suppose this is the body and it is kept in contact with two reservoirs. Second. Okay. So it is kept in contact with two reservoirs, and in both the cases we are having that the body is having a initial temperature of 100 degrees centigrade and the final temperature is said to be 200 degrees centigrade. Okay. Okay, and we have to find out the entropy change. Here we have to remember that our entropy is basically a state function. So it means it only depends upon the initial state and final state. It is not a path function. Path means how the heat is being transferred doesn't matter. Because in the first case, we are having two reservoirs. So heat is being transferred using two reservoirs. Okay, because it is not mentioned actually how the body is kept, but it is my guess, or suppose this is the body and it is kept in contact with two reservoirs sequentially. So this is our reservoir 1 and this is our reservoir 2. This is my understanding. And in the second case, same body, but now it is having 8 reservoirs. Okay. So this is first, second, third, fourth, fifth, sixth, and this will be our 8th, 7th, 6th, 5th, 4th, 3rd, 2 and 1. Okay. So this is reservoir 1, 2, 3, 4, 5, 6, 7 and 8, and this body is in contact with them. In both the cases, the initial temperature of the body is 100 and final temperature is 200. So how the heat is being transferred doesn't matter. Only is what is the final states. Final state in this case it is temperature, state is temperature, so it is 100 and 200 degree centigrade. So we can use the direct formula that our entropy change of the body depends only on initial and final states. Therefore we can write entropy change of the body will be equal to integration initial temperature, final temperature C and our dt divided by T. Okay. And from here, if we integrate it, C is our constant and this comes as natural log of our Tf upon Ti. Okay. C is given to us as 1. Therefore, we can say that our delta S body will be equal to natural log of our Tf upon Ti. And in both cases, final temperature is our 200 and initial temperature is our 100. Therefore, we can say that our delta S body for two reservoirs will be equal to delta S body for 8 reservoirs will be equal to natural log of 200 upon 100, which gives us natural log of 2. Okay. So in both the cases it will be natural log of 2 and natural log of 2, so option B is correct. B is correct. So this completes all the, B is correct. So this completes all the question. In this part we did some questions for year 2014. We did advanced questions, and from the 2015 we solved 2 mains question and 4 advanced questions. This completes all the questions. Thank you.